Ooh, it's starting. Okay. So, that was a good thing. Yay! All right, so Unit 1, that was the unit that we just did. Good for us. What did we talk about, Unit 1? What was like the premise? Like we did error, we did that stuff, but like the big thing that we talked about, what were we talking about?
Non-accelerating
What's that?
motion.
Forces, and what'd you say?
Non-accelerating motion.
Yeah, so forces and non-accelerating motion. So non-accelerating motion means that acceleration, well, I guess by definition is 0, right? So I guess we can say that. And in conjunction with that, in terms of forces, what did we know for sure for every single question that we worked on? What's that? They were equal, and so therefore what, Grace? The net force is 0, right? Does that work for us? Okay, so we can say that the acceleration was 0, so we knew that the net force was equal to 0. Yeah, is that right? Yeah. Is equal to 0. Sorry, I'm getting excited. I'm getting ahead of myself. There we go. That's better. I was really excited. I'm really excited about Unit 2. Do you know what happens in Unit 2?
Accelerating.
We're going to accelerate stuff. Yes! This is, I mean, not that Unit 1 was unexciting. I'm not trying to imply that. But in Unit 2, here we go. We're talking about forces and motion, but it's going to be accelerating motion. So in these cases, F net will not be 0 anymore. Woohoo! And as a result, what do we know about the motion of our objects?
They're moving.
Not only are they moving, because did we have situations where things were moving
They're
up here?
gaining speed as they move, or accelerating as they move.
They're accelerating as they move. So in this case, acceleration is not equal to 0. There's my not equal to. Sorry about that before. Is this okay? So this is really where we're going to play today. But to kind of get our brains in this, also, I wanted to introduce you to these new questions. I got this book. I think this book is so cool. I hope you guys love it too. It's full of like all of these problems that make you think. Yes. So they're not just like plug in numbers and find out what comes out. Like that is not really fun. These are like thinking problems. So we're going to work through a bunch of these today. I may have gone a little bit overboard when I listed them for today, because we have like 8 of them that I want to do today. I won't do 8 of them every day, but they're just, and you know, you need a good introduction to them. So we're going to start with that, and then we'll come back to actually defining that stuff in just a second. So here we go. First one, let me kind of explain to you how these problems work. So they have kind of a setup and a picture, and then they ask you to do something. So I'm going to read this out loud just so that you can see it, you know what's going on. So various packages with different masses are moving at a constant speed on a conveyor belt. At the instant shown below, all of the packages have the same constant velocity of 2 meters per second directed to the right. So that's the little like vector arrow up here, right? The packages do not slip on the belt. All masses are given in the diagram in terms of m, the mass of the smallest package. So E is the smallest. It has a mass of m. D is 5 times the mass of m. It's 5 times as big, etc. Does that kind of make sense? So it kind of gives you a setup, and then it asks you to do something. In this case, it says rank the magnitudes of the magnitude of the net force on each package. Okay? So these sometimes will require a little bit of math, but it's not going to be big, like lots of things. Sometimes they don't. I'm going to give you a minute to take a look and think about this, just you and your brain, and then I'll let you discuss in just a moment. Does that sound okay? Okay, so take a look and think through this. See it in the back, okay? Can you see it? Okay. Okay, and so the game is here that you're gonna rank them. So like from biggest to smallest, or if you think they're all the same, then you would check that box. Or if they're all zero, you check that box. Or, and some of the time, it will give you not enough information. So if there's not enough information, then obviously it cannot determine. Okay, so go ahead and discuss with your table partners. See if you can come up with an answer.
DBC, because they each have greater inertia with the mass of them.
Yeah, that's what I was
Okay.
Oh, it's like force it. So it's just it's like I can force the stop.
So they should have a greater inertia.
But could it be
Yeah.
What are we doing?
I think we got it.
Let's do it, okay? Think you're ready? Maybe? Yeah? All right. Who wants to share an answer? Otherwise, I get to pick somebody. Go, Daniel. What'd you guys say? And before you even say anything, I'm not saying you're going to be wrong, but I just want to remind everybody that it's okay if you are wrong, right? We're learning, and that's a good thing. Got to put something out there so that we can talk about it. Go ahead.
We were kind of undecided, but I was also thinking it could be all zero because there is no acceleration.
Okay, so tell me more about what you mean.
Force equals mass times acceleration. It says they're all.
I haven't seen that anywhere yet. I want you to use what we know already. Tell me based on what we know, because I haven't used that equation yet. You may have last year, another time, but you're on the right track. Just keep talking and based on what we know already.
It says they're all traveling at the same velocity, so it's not changing velocity. Therefore, there's no acceleration.
Okay, that makes me happier. Keep talking. So the acceleration is zero, you saying?
Yeah.
Okay, so what does that mean?
I mean,
The force is equal to zero.
The what force is equal to zero?
Oh, the net force.
The net force is equal to zero? The net force for what is equal to zero?
For the package.
Yeah. For package A
For all the package.
and for package B, right, for all of them. What are you thinking about, Caleb?
I was just thinking how it's probably easier to stop something lighter than something heavier.
Okay. So what? So keep talking.
Well, I didn't know this, but I just, it's like that sounds right. But I just kind of like interpreted it as like it's easier to stop something that's light, as in like an object in motion wants to stay in motion.
Okay.
So with more mass, it's going to have more inertia. So it's going to have more like, if it's moving forward, it's going to keep moving forward. So it's going to take more force to stop it.
Okay.
With an object with less mass, has less inertia, so it would theoretically be easier to stop it.
Okay. Do you guys agree with everything that Caleb said? Okay. What result does that give you for the question? Remembering that the question says rank the magnitude of the net force on the package.
Yeah, I guess if it's net force, then I guess they all are just zero.
He says with confidence.
I missed the step.
That's okay. It's not bad. You're doing fine. Daniel, I saw your hand.
Yeah, he explained it. I was going to say that they each some have more momentum than others because there's more mass.
Sure.
However, what the question's asking, it doesn't involve momentum. So if they're all traveling at the same velocity with no slipping, the acceleration is zero.
Does that make sense? The reason I like these questions, on the face of them, they seem pretty straightforward, but they're kind of deep, right? There's a lot more to this question than just saying that. But really, because there's a lot of stuff that we have like ingrained in us. Does that make sense? Like these intuitions that maybe something should be one way or another. But I like this because we have to like really think back to what are the basic physics principles that we're talking about, right? You know that these are at a constant speed of 2 meters per second. If it's at a constant speed, you know it's at a constant or acceleration of 0, right? we know that if the acceleration is 0, the net force has to be 0. Is that okay? Is that, I'm not quite getting a happy reading yet. You feeling all right? Can we try another one? See if another one is, I think we can kind of use this process to continue. So it should be all 0. Just clarifying to make sure that we're all on the same page there. Sometimes they have really cool pictures like these. I love these pictures, right? All right. Water skiers are pulled at a constant speed by a tow rope attached to a speedboat. Because the weight of the skiers and the type of skis they're using varies, they experience different resistive forces from the water. Values for the resistive forces, RF, are down here, okay? And for the speeds are given as well. The question says, rank the magnitude of the net force on each water skier. So we give a couple minutes to think. Have a conversation.
But also,
Yeah, because I was about to say,
the acceleration is 0 and that force is 0.
it's just a lot of things.
Because if they're all just moving at that, then you can just pretty much negate the resistive forces. It doesn't matter.
Different velocities.
The resistive force would only play a factor if there was acceleration.
Still all going at constant velocities. So
But they're constant, so it's 0 again. Yeah? Okay.
All right, are you ready?
Chemistry.
They are. All right, who's got an answer? Go, Daniel, what are you saying?
I'm gonna say it's all 0 because they're all staying at the constant velocity. Because A is staying at the constant velocity of 4 meters per second and B is at 6 and so on.
Okay.
So since their velocities are constant, the acceleration is 0, therefore the net force is 0.
What do you guys think? Does that seem reasonable?
Yeah.
Is that what your gut told you at the beginning of the question?
No.
Yes, maybe, I don't know for sure. Does it seem like they should be different since their velocities are different?
It would only
Maybe. What's the key word here that's making them
constant.
constant speed, right? Constant speed and net force. Anytime you have a constant speed, your net force will be 0. Anytime you don't have a constant speed, your net force won't be 0, right? Okay? That's the key. That's really what we want to pay attention to. Now, I do have to tell you, based on this small sample size, we would assume that every single time we have a ranking test, the answer is all 0. That's not the case. So don't get, oh, I know the answer to every single one. But, yeah.
I have a question.
Please.
So, what if it asks you the net force that is perpendicular, parallel to the surface of the water?
Okay. So you're saying, what is the net force of the skier just in the parallel direction?
Yeah.
What do you guys think? It's a good question.
Wouldn't it also be 0?
Why?
Because it has to overcome the force of the 750, so wouldn't it just be the same? I don't know.
I think you're on the right track. Let's draw ourselves a free body diagram. I feel like a lot of times when I tell you to draw free body diagrams, it's like, oh man. But I'll tell you on questions like this, it's much easier if you actually do, because then you can see what's going on. So let me ask, what forces are acting on the skier? Raise your hand if you can tell me one. Go.
The bolt.
Yeah, like along the string.
Yeah.
Okay, so the force of the boat on the skier. What else? Gravity. Force of the earth on the skier. What else? What else?
Water resistance.
The water. Which way is the water pushing or pulling?
Against the skier.
I say like half of you going up and half of you going that way. Because they're going both, right?
Yeah.
Yeah, absolutely. So there's some going up. The force of the water. That's a buoyant force. That's fun.
We're gonna learn about that.
Next year. We wouldn't do it this year.
Okay.
Yeah, it's kind of. I wish we could. Cause maybe if we have extra time, we'll do it because it's fun. And then this is the resistive force, so that would also be a force of water. Now, if we look at these, they have to all add up to what? 0. The two in the up and down direction, how do they compare?
Yeah, 0.
They're 0, because if one of these, let's say that one of these was bigger. If this one was bigger, where would the object go? Up. That doesn't happen, right? And if this one was bigger, then he needs a snorkel, yes? Right, like he's going down. Okay, now, so these guys are adding up to 0, so they're the same. What about these two here?
Also 0.
If this one was bigger, then 750 is this way, right? If this one's bigger, then what's going to happen to the person?
Shoot past the boat.
Accelerate that way, right? Or if this one was bigger, then accelerate backwards, even though I don't know how that would happen, so let's not pretend that's it. Does that answer your question? Okay, awesome. Thanks for asking it. Yeah. All right. I think I've got one more of these to do right now. Oh, this one's a good one. Here we go. Blocks attached to the wall. 2 blocks are attached by a rope to a wall. A child pulls horizontally on a second rope that's attached to each block. Both blocks remain at rest on a frictionless surface. The weights of the blocks and the magnitudes of the forces exerted are given by the child. Are given. Woo! I'm tired. All right. So there are the pictures. I give this to you. Rank the tensions in the ropes. So I'll give you a minute to take a look. See if I can make this one a little bit bigger for you. There we go.
Do we have to make a free body diagram?
Go ahead and talk about it. This one's kind of a chunky one.
I think it's asking what forces are acting on the rope from when and where.
Because you have 8
Like I think.
Wait. Oh, there's A, B, C. Okay, there's
Does that make sense?
Probably
Yeah.
be
Yeah.
graded.
Yeah. So 4 ropes. Yeah.
It'd probably be A, C, D, B. I don't know.
Why would the tension
Why 60?
on A be bigger than the tension on C?
Because 80.
And again, it may be helpful to draw a free body diagram.
Pulling it also.
We love those free body diagrams.
Yeah, I mean, more time. Oh, it's greatest least, right?
C. Yeah. So
C.
C.
C is a total of 80. A is a total of 80.
And if you have some that are the same, you can say that things are equal. That's okay.
80 plus 20.
No, but
Oh, you're talking about just like the box
but the
alone?
box is at rest.
Is it?
So 50 and then does that come into my
Yeah, they were made at rest.
C?
Okay.
Does that mean that they don't have?
Because isn't it like also the
Yeah.
pull force also affecting A along with the
That's what I'm
block?
saying.
I think it.
No, it says it remains at rest.
Okay. Okay.
Both blocks remain rest. So A and B,
Okay, I'm gonna say B, C, and
C and D.
Okay, I'm gonna say A, C, B, D. Wait, no, I'm gonna say A, C.
It's A, B.
Well, if I think I'm right, A and C, then B and C are the
A,
same.
B is equal
Which I
to
don't think is right.
Alright, I got it.
A has to pull A
but
back.
it's at rest.
Yeah, I don't know.
How's it going?
Are they
acceleration.
All right, let's take a look. Let's kind of work this through. Does anybody want to give me an assertion, a guess, a starting spot? Daniel's told me 2 already. Is there anybody else that wants to play? Yeah.
So we said A, B are equal, and then C, D.
A and B are equal,
And,
and they're
C,
greater
D.
than C and D.
Yeah.
And how are C and D? Are they the
equal.
same? Okay. Other thoughts? Go.
Does the box being at rest make a difference? It's like the 80 newtons that the child is pulling on B.
Mm-hmm.
Would that affect A? Because it's at rest. I don't know. Just a thought.
Okay, so you're saying, like, the fact that the child is pulling on B. So Rachel, let me ask you a question that may help to ask your question, but I'm not sure. What if the child pulled instead of with 80 newtons with 90 newtons of force?
It would have to resist more.
What's going to happen?
It would have to resist more.
What's it?
Force? The box.
The box. So, but there's no friction. So friction isn't doing anything. So, but there is an it. What it is she talking about? What?
Gravity?
Rope A.
Rope A is going to have to pull back more, right? If we think just about what's going on in the 20 Newton box, you've got a force of gravity, right? We'll just call it FG. I'm going to be lazy here. And this is a normal force. And you've got this applied force here.
The other than it just snapped.
And then you've got this force here. We'll call it a tension force. Is that okay? What do they have to add up to?
They have to equal each other so they don't break each other.
So all of them have to add up to 0, don't they? I mean,
Yeah.
that's kind of what you're saying, right?
Yeah.
So these guys, whatever, blah, blah, blah. If this is 80, what does this have to be?
80.
It has to be 80. And if this is 50, that has to be
50.
50. Yeah. So this is what I would say as well. Okay. There's one other way that I would also accept this. If you were looking at direction, if you were worrying about the directions as well as the magnitudes, then you might say that A is the biggest, and then D, and then C, and then A. Does that make sense? The reason that I point that out is that when you have questions like this that I give to you to fill out and turn into me, there's this beautiful space down here that we've just been talking in, the explain your reasoning space. But I'll tell you right now that if you just put this and you don't tell me why, I wouldn't give you any credit because that might just be a really lucky guess. Okay? So you need to make sure you explain it. And if you said A and then D and then C and then B, and explain to me that you were including the direction, then I would count that correct. That makes sense to me. Okay? There is often more than one right answer when you're talking about a qualitative thing like that. Okay. We doing okay? Yeah? Okay. I want to do a couple notesy things and then we're going to come back and do a couple more of those because they're just so good for your brain. Okay, so Rachel was thinking about it. I promised that we were going to talk about net force not equaling 0. But all 3 of the problems we just did, the net force was 0. It's like I'm lying to you all, right? Like that's not fair. So we want to get to this place where we actually are talking about net force not being 0 and when things accelerate. So the question there, because usually if things are accelerating, then the questions say, well, how much are they accelerating? So that means we need to figure that out, right? So the question that we're trying to answer right now is, what factors affect the magnitude and direction of an object's acceleration? That's my question to you. What things affect the magnitude and direction of an object's acceleration? What you got?
Force.
Force. Okay, what'd you say?
Force.
Force. You said force, and then you said
Applied force.
applied force.
Force
And then I asked you again, and you said force. So tell me, what do you think it is?
Force in general.
Force in general, just the force. Like,
Well,
I'm picking on you because I want to know more. That's why.
there's a lot of forces that go into it, so I was just putting them all together. Like there's the applied force, there's the force of friction, there's force of gravity, and there's force of normal.
So when you put all those together, what do you get? The net force, yes, and that's the one that really matters. That's the one that really matters because this frog has been sitting on this table for a long time. And he doesn't accelerate. He doesn't go anywhere because the net force is always what? It's always 0. Now I move him over here. Oh, it's like, yay, thank you. And I let him go. Has gravity changed? No. But he accelerates anyway because the normal force is gone, so the net force is now 0, right? So it doesn't matter what the applied force is because, I mean, think about it like this, right? Can you calculate the acceleration of the table right now? It's 0 because it's not moving, right? So, but I'm applying a force of 4 newtons. I apply a force of 7 newtons. Can you calculate it?
0.
It's right, but like, you know what I'm saying? Like, it's not the applied force that affects it. It's the total overall, it's the net force that affects it. So, I'm going to say here, what factors? Absolutely, F net affects what does it affect? The magnitude or the direction? Both, right? If the net force is to the left, the acceleration is going to be to the left. That's your left, okay, good. If the net force is down, the acceleration is going to be down, right? And the size of the force affects the amount of acceleration. Is that logically making sense? Okay. Right, so F net, I agree, affects the magnitude and the direction. What else might affect the acceleration of an object? How much? You don't get to talk anymore because this is like the Daniel show. I want more people to play. I want you to think, guys. What else might affect how
Friction.
much something is going to
That counts as
accelerate?
force.
What's that?
That counts as force.
That's part of the net force, yeah. So forces are kind of off the table now.
An object's mass.
An object's mass. What do you think about that?
X magnitude.
Affects the magnitude of the acceleration? So if you don't believe that, and it doesn't seem to seem inherently obvious to you, you could think about maybe 2 balls. Like maybe you have a basketball and a bowling ball. Okay? They're about the same size, but probably not the same mass. Unless you have a really, I don't know, extreme something. Okay? If they're both sitting at rest and you want them to move, that means you're going to get them to accelerate, right? And in order to do that, you have to apply a force so that the net force is not 0. Okay? If I apply a 3 Newton force to the basketball and the same 3 Newton force to a bowling ball, will they have the same motion? No. What's going to happen? What's going to be different, Zoe?
The basketball will probably accelerate faster because the mass is or less than
Love it. Don't have to say probably. They will certainly. The basketball will certainly accelerate more, right? Because it has much less mass. Absolutely. Is this making sense to you all? Those are the 2 big ones. Let's do it. So we're going to write this down. Now, as F net goes up, what happens to the acceleration?
It goes up.
As F net increases, so if I have a bigger net force this way, what's going to happen to the acceleration?
Go up. That way.
I hear people saying up and down.
It goes up.
Okay, hold on, let's do this. Here's my frog. If I have a big force this way and a little force this way, what's going to happen to the frog?
Right.
It'll go
It's
right.
going to go that way. Now, what if instead of that force, I really want to erase. Oh, there we go. I have an even bigger force. What do you think is going to happen to him? I'm going to push harder. What's going to happen to his acceleration?
It's going to go more that way
It's
faster.
going to go even more. Does that make sense? Right? The harder that I push, the more acceleration it's going to have. So yeah, as F net goes up, the acceleration is going to go up. So I'm going to say that they are proportional. That little sign means proportional to. Now, what's up? You want to tell me the next answer? Is that what you want, or you have a question?
No, that's what I was gonna do.
Let me pose the question first. As the mass goes up, what happens to the acceleration? That one goes down. Okay, does that make sense, Carmen? I think that's maybe what you were thinking of. Is that maybe? I don't know.
Yeah, I think so.
Yeah. So as the mass goes up, so we're thinking like again, bowling ball versus basketball. Bowling ball has more mass. The acceleration is going to be smaller than the acceleration would be of the basketball, right? So can I say that, oops, excuse me, go away please, thank you, that M is proportional to A?
Inversely.
Yeah, that's what I wanted. Inversely, how do I represent inversely? What's that? Is that what you wanted?
Yeah.
It's gone. No, that's not the right answer. How do we represent an inverse proportion?
What if
Anybody
we
know?
just like write the proportional sign backwards?
You know, we could do that, but I don't think anybody else would understand it.
Like 1 to the -1.
To the -1 or 1 over, same deal. I'm going to write it as 1 over just because I like denominators, unlike some people. I don't know, some people get afraid by them. It's funny. I laugh at them. Okay. So now, as the denominator gets bigger, that means this whole number gets smaller, and that thing is proportional to A. Is that all right? Okay, so we're going to put them together. Here we go. So that means that acceleration is directly proportional to net force. And my friends, I have to reiterate this over and over and over. This is the most important part. The net. It has to be the net force. It's not gravity, it's not applied, it's not normal, it has to be the net force. Because if the net force is 0, what do you know about the acceleration?
0.
It's 0, right? Are you with me here? So that has to be net every single time. And I want the M in the denominator, and then I'm going to put a big box around that because that's important. Okay? The acceleration is dependent on the net force and the mass. Is that okay? Okay. Questions about that? Now, could I have told you this in Unit 1? Does this match with what we were thinking in Unit 1?
Yeah.
Can somebody tell me why you're saying yes, besides because it seems like a good answer?
F is 0, A has to be.
Yeah.
Say again?
Because if F is 0, A has to be 0.
Right. If F is 0, A has to be 0. That would be Unit 1. So now we're saying if F net isn't 0, A wouldn't be 0 either, right? That's all we're saying. Life is good. Good show. Good show. Okay. Let's see here. I want to try this problem. It's another ranking one, but it's not asking for net force this time. You're welcome. Yay! Mixing it up, making it more exciting. All right. This says various similar boxes are being pushed for 10 meters across a floor by a net horizontal force as shown. So this is not an applied force. This would be the net force. Does that make sense to everybody? So you could say it's a frictionless floor and then that's just an applied force. That's okay. But you have to remember that's net. That's an important thing. Should have even told you that. Now I'm giving it all away.
Yeah.
Okay. Blah, 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 blah. All the boxes have the same initial velocity of 10 meters per second. Asks you to rank the accelerations. Go.
Can you zoom in on the boxes?
What?
Can you zoom in on the boxes?
I would be happy to, yes.
Can I go bathroom real quick?
I'm not sure if you can see what it's
Is that better, Jack?
Yeah, that's perfect. Thank you.
I'm not sure about the S. All I know is B is C and 370.
Yeah, so
Is the last one 15?
15, the D,
Yeah.
15 kilograms, yeah.
All right. I gotta go base first. And probably in ABCD. All right. Yeah, I can agree with that.
I think
I was just not volume. I knew the first one.
yeah, CB.
Something B is
No,
I trust
it's
your math,
fine.
yeah.
Like, you see, okay, so like the
Maybe that was
behavior
my lie.
for
So
C
that's
will be
physics.
15, so 15 will be 4 over
Are you ready?
5. Yeah.
Maybe perhaps? All right. Nick, I haven't talked to you all day. Do you have an answer? Or you have a proposition for an answer and we'll try it and then we can, I mean, it's not.
Well, we said A would be the greatest acceleration followed by D, and then it would be C and then B.
And they're all bigger than one another?
Yeah.
What do you guys think? Do you agree? Can you tell me where that came from? Was it just a guess or were there?
It was because since there's the biggest difference between 100 and 15, so it'd have the greatest, like, it's like, because you have the biggest difference, you have the most force. I know what I'm trying to say, but it's like,
We can, it's totally fine. Andrew, can I tap you in? What do you, what, yeah.
I think what we were thinking was just like a bunch of ratios. So since
Okay.
we know force affects it acceleration directly, the higher the force, the more acceleration, and the lower or the smaller the mass or less mass, then the less it will drop the acceleration. So that's why we put A before D. And
So A before D because they have the same force and A has less mass. Awesome, okay. Keep talking, either of you, okay.
For C, I put C before. I thought, I'm not sure, but I just thought about since you're just pushing or putting more force. There's the bigger net force. So.
yeah.
Okay. What do you guys think? Does that make sense to you? Yeah, I think it's all about ratios. Physics is all about ratios, right? That's really what it is. Like, can we plug in numbers? Sure. But really what we're trying to figure out is how things compare, how things are different. So that's exactly what you want to do. You know that as F gets bigger, A is going to get bigger, and as M gets smaller, A is going to get bigger, right? Okay. You could even look at it literally if you wanted to as F over M. And you could even just plug them in. Now, I like the fact that you guys didn't just jump to doing that, but you were actually kind of thinking it through. I'm not saying that if you did plug it in, that's a bad thing. I really am not saying that either. But I want you, I guess the reason I say that is that I want you to start thinking of things without having to run to your calculator every 5 seconds. That's what I'm saying, okay? Because it makes you a healthier physicist, and that's what I want. So does this match with what everybody else had? Did anybody want to discuss more? How are we doing back there? Are we happy? Cool. All right. All right. So now I want to throw in some more numbers to this game. Okay. So all of the problems that we've done so far have been ranking problems. So I want to actually let's do a for real one. This first one that we're going to do is we're back to the mystery box. Do you remember the mystery box?
Yes.
Caleb was like, I don't remember the mystery. It was the day that you were gone. It's that day. So it's a box with something mysterious in it. Isn't that exciting? You don't know what it is, so it can be whatever you want. And the story goes, Caleb, so that you know, that the first problem, we just had the mystery box and it was sitting on a table, right? And we had to find the gravitational force and the normal force. And then the second story, or the second part of the story, was that your friend pushes down on the mystery box and you had to find the normal force. And then your friend pulls up on the mystery box and you had to find the normal force. It was so that we could play with normal forces. Now, same mystery box. But now instead of just pulling up on the mystery box a little bit, your friend takes a hold of the bow and pulls up on it with a force of 100 newtons. Oh my gosh! I'm serious, it's weird. Why would they do this? I don't know. I want to know what the acceleration is of the box. And what I want you to do is to do this with good physics process. So I want you to draw a free body diagram. Write down an F-net equation. Daniel's laughing at me like, oh my gosh, free body diagram for real? Yes, because it's going to get harder next. And I want you to get used to it now so that when they are harder, you don't sit and cry. Because that's sad. It is, right? It is sad. So draw your free body diagram, write down an F-net equation, then we'll regroup. Acceleration. Find it.
Acceleration up.
Acceleration. Find it. I mean, yes, but you shouldn't need for me to say that to you. You know what I'm saying?
Yeah.
All right, let's write down forces. What forces are acting on the box? Perla, what's one of the forces acting?
Gravity.
Gravity, right? Which way does that one go? Down. Like, oh my gosh, we not answered this question a million times. Yes. But it's healthy. Every time. Every time. Free body diagram, every time. What's another force, Carmen?
The 4.
4 on the box. Like a normal force, is that what you mean? Okay. Any other forces acting on the box? There's an applied force, right? The force of your friend or a person. I guess I don't know. We don't know if it's a friend or an enemy. Okay. Free body diagram? Check. Next thing is what? The what?
F-net equation.
F-net? Is that okay? And we kind of play our givens in there, so yeah.
Okay.
Probably givens are good too, but yeah. All right, Jack, if I was going to write down an F-net equation, what would it say?
Well, F-net would be FG
Okay?
minus, well.
Let's just add them.
Alright, let's add
Let's just add them, and then we'll put negatives in later. Is that okay?
Alright, plus F, A, and F, I suppose. If we're gonna just add them.
I suppose. Okay. And the net force, now we haven't actually said this officially, although Daniel did kind of give it away earlier. We have acceleration is equal to F net over M, but we don't have anything in terms of acceleration. We have it in terms of F net, so we need to solve that equation for F net, right? And that's what did that say? I don't know, that's weird. Anyway, whatever. So F net equals MA, yes? So then I can write MA here, which is helpful since, what are we looking for, Rachel?
Acceleration.
Acceleration. Hey, see, there it is. That's how this is beautiful. Okay, so we want to know this. Do we know FG? Yeah, it tells us that, right? 98. So we wrote that down in our givens, good for us. Do we know the applied force?
Yes, we do.
Yes. How big is the applied force?
100.
100 newtons. Now, do we know the normal force?
No. Kind of.
It's
Because it's
I
like,
can't float the ground.
Why?
because there's more force in up direction and down direction. Then it's not touching anything.
Does that make sense? So remember when we talked about the normal force, right? It's not like one of those things that there's an equation for. It's just going to, it will vary depending on what else is going on. So if there's no reason, if this thing is accelerating upwards because of just these other two forces, the applied and gravity, then there's no reason for that box to be touching the surface. And if it's not touching the surface, there is no normal force. Does that make sense? Okay? So I don't have a problem with you having this on the picture because initially when I'm thinking about it, like, well, yeah, it was sitting on the table, right? Like that seems logical. But then we need to think it through and say, okay, but wait, hold on. This was 100, this is 98, so it's going to accelerate upwards. If it accelerates upwards, no more table, no more normal force. So I'm just going to throw it away right here. What's up, Caleb?
I guess it's probably like the next step. I don't know. Like, is gravity negative? Do we write them as given as a negative?
Yes, we will put it as negative. So let's go ahead and add some more stuff here. So we've got negative 98 newtons plus positive 100 newtons is equal to, do we know the mass of the object?
No.
98.
It's not terribly apparent yet, but we can find it, can't we? Because we know that Fg,
Is equal to mass times acceleration.
isn't that the truth? Right? And you know that this is 98, and you know that G is 9.8. 1 or whatever, right? So what's the mass?
10.
Whoa! Remember we had that 10 kilogram history was same one, right? Okay, so we'll remember this is 10. And then we can find A. Now we can probably even use a calculator, because we don't need a calculator to subtract 98 from 100, right? We can do that. And then we can divide that by 10. And probably we can even do that in our heads to get an acceleration of how big?
Or 2 square.
It's true. How are we doing? Was that okay? Okay. So a little more work involved in writing this all out. Not necessarily, but I want you to do it so that you're getting the process. I want to look at this and see if I still want to do this problem. Yeah, I do. One more of these. I told you I went a little overboard, but it's good for you because you're learning so much. Yay, learning. Okay. Can you see that? Is that big enough or no, we want it bigger? Bigger. Bigger. How about that? Two forces act on a block that's initially at rest on a frictionless surface. It says rank the speed after 3 seconds. Now, have we talked about how to calculate speed?
Yeah.
If it's accelerating in this room this year? No. I mean, you all have seen it, but, and I don't want to do that right now, but how can you extrapolate from what you know? If it is going as the fastest after 3 seconds, that means that it has the biggest what? Say it. Acceleration. Yeah, so go ahead. Okay. So why don't you take a look by yourself first, and then I'll let you talk to each other. Okay, talk. Discuss. Draw some pictures. Do what you need to do.
What?
I disagree.
Why?
A is the highest because
DC, yeah.
it has an excess of 2 and its mass
Well,
is
these
bigger
Yeah,
than
but
O.
sorry.
Going in that
Is equal to
direction.
zero.
So how
I
much?
mean, C has to be
So as mass increases, acceleration
D
decreases.
has to be.
If you're turning direction,
So it would be logical that B and C would go faster.
It's just, it's still more.
They both have the same
Right.
as A and B. They both have the same.
but D is 0.
Then it comes to
C accelerate the same as B.
Alright.
Yeah.
B and C are equal.
Yeah.
And it's a different group.
I guess you can go either way.
They give us.
I was thinking like that.
It just says speed and doesn't say velocity. So
Well, I think that's what we're doing.
It depends what you
It's
count
just
as
a-
a positive direction.
That's how. It's, yeah.
You come up with the answers?
Yeah.
Yeah? Do you guys all agree? We talked together yet or not yet?
Yeah. What, you mean like this entire class or like?
Yeah.
I got that.
I thought maybe you would just do that.
Same as B.
All right, Grace. You ready?
Sure.
What did you guys say back there?
Okay, well, A and B are moving at this, like, it's the force that the F net is 2.
Okay. For both of them, right?
Yes.
Okay, I'm gonna write that down. That's good information. So F net is 2 here and it's 2 here.
And it's -2 for C
Okay.
and 0 for B.
Okay.
Okay.
Awesome.
And then for A and B, to find which one's going faster, you have to look at the mass. And because B's mass is lower, it would be moving faster.
Does that make sense to people? Okay, so are you saying that B should be the
1.
number 1? Okay.
And then A, and then D, and then C.
And then A, and then D, and then C. And they're all not equal. Is that what you're saying?
Yeah.
Okay. Cool. Do you guys all agree with that? Yeah?
Well,
Go,
it
Nick.
it says speed, so velocity doesn't matter which way it's going. So wouldn't B and C be the exact same?
Okay, so you would advocate for
Yeah.
B equaling C?
Yeah, B equaling C and then A and then D.
What do you think?
That works too.
That's what I think. It just depends on where you put the negative and the positive.
Right. So I would tell you that if I was grading this question, I would probably give you credit for both of those as long as you were articulate. I would say probably because it does say speed. And so if you were getting really, really about things, then this one would be more literally the speed is rated there. But I think the thought process is perfect. You did exactly right. So I would take either one of those, again, as long as the reasoning was there. Yeah, that's cool. Are we getting the hang of these things?
A little bit.
So like if they show up and you do them for like whatever, that would be okay? All right. One more problem for today. Are you ready? No! That's the last one of these.
What?
I'm going to give you a big chunky problem. Not a ranking task problem. A real question, not that one, this one. Here we go. 2 boxes A and B are connected by a lightweight cord and are resting on a smooth, frictionless table. The boxes have masses of 12 and 10 kilograms. A horizontal force F sub P, I'm not sure why it's a P, of 40 newtons is applied to the 10 kilogram box as shown in the picture we're going to draw right now, okay? Because I didn't want to copy the picture. So here we go. We're going to draw our boxes. So there are our boxes. They're attached by a lightweight cord. And then there's an applied force, F sub P. So I'm going to say FP on, we'll call this one box A, and this one box B. This one is going to have 10 kilograms of mass, and this one has 12. The only reason I know that is because it says that the 40 Newton force is applied to the 10 kilogram box. Does that make sense to everybody? So the 2 questions are, number 1, to find the acceleration of each box, and then number 2, or part B, to find the tension in the cord connecting the boxes. So, I want you to work on this for a little bit. I'm going to let you guys discuss. You're going to start with doing what?
Free body diagram.
Free body diagrams, favorite thing. And then you're going to do what? It's the second thing we always do, friends.
Right.
F-net equations. There you go. Of course. All right. So I want you to chew on this for a little bit, and then we'll discuss
What can we
it.
do, Caleb?
Go, go, go. Yeah. Yeah.
together.
We're going to talk about that. So, do what you think is right first, and then we'll talk about it. The answer is yes to your question.
Just gonna answer this. Okay. If we know there's acceleration, would the tensions in the string still have to be the same? The only thing they have to overcome is normal force? Assuming that it's straight parallel to the ground?
Say that again.
For the cord not to snap, I'm guessing that no, one mass is greater.
So imagine that
I don't know
Mary
what I'm
has two
thinking
little
anymore.
blocks, right?
Yeah.
That are connected by a piece of string. She's pulling on them.
Mm-hmm.
Okay. So if she's pulling on them, there might be some tension in that string.
Yeah.
Right? Because the thing is accelerating all the way.
Mm-hmm.
Yeah. So tell me your question again.
Would the force P would be the same as the tension in the string? Because if they weren't the same, if force P was greater than the tension in the string, would the tension in the string snap?
Not necessarily.
Okay.
Not necessarily. Because it says, it implies that they're accelerating. And if they're accelerating, then this guy's got to be bigger than this one. If you're just looking at the forces on it.
Do the accelerations have to? No, accelerations can't match because one has a greater mass than the other. Can you use what you find for A to find the answer for B?
Yes, you will.
Okay.
Tension is a force. Yes?
Because you need to find the force that's acting on box B by finding the acceleration that's acting on A, which would be the force that's acting on B.
I caught half of that. Say it again.
I don't know. I want to.
You don't want to say it again?
I don't know. Can we just do this?
Yes, we can. I'm going to start playing. If you guys want to keep discussing it, it's fine. If you want to play with me, that's cool too. So we need to look at what forces are acting, right?
Yeah.
In the y direction, I'm just going to give you these ones. So this is FG on A. Or I don't like this. I got to do it right, otherwise I'm going to be sad. Earth on A and table on A. Earth on B. Table on B. Is everybody okay with those? What other forces are acting? Anything else?
The unknown force on B.
What's that?
FP on B.
So so this is where it all comes down here. Is FP acting on B?
There's a
Not what?
Not directly.
Not directly. They're not in contact. And remember, and we haven't actually talked about this year. I probably should have. There are four fundamental forces, right? Those spooky action and distance forces. Do you remember me talking about those a long time ago? Gravity, electricity and magnetism, strong nuclear, weak nuclear. Those are the only forces that are allowed to act not in contact. Okay? So if FP is acting on B, it would have to be through one of those mechanisms. It's not. Right? Does FP have an effect on B?
yes.
Sure. Through what?
Tension, because A is blue.
Tension, right? So there's a force on B, but where does the force on B come from? Does it make sense that it comes from A, like through tension?
Mm-hmm.
Yeah? And is there a force, another force on A?
Yeah.
Force. Oh, box B is on.
Box B is pulling on box A, isn't it?
Yeah.
Sure. How does the force of B on A compare to the force of A on B?
It's greater.
I'm not going to hit you. He totally thought I was gonna hit him. But I would never do that. I'm handing him the meter stick. All right, so we're gonna pretend this is a rope, okay?
Okay.
I'm gonna pull on it.
All right.
If it doesn't slip out of your hands, that means you have to pull on it too, right?
Yeah.
Right? Because if it did, then I'd go flying, right? Does that make sense? Okay. So I'm applying a force to this end, force of carbling on Caleb, right? That's you. And as a result, he's applying a force, the force of Caleb on carbling. It's a Friday. The 8th graders are excited. It's like a thunderstorm of 8th graders. Okay.
But one of these forces has to be greater than the other for like one to move, right?
Does it? Does one of the forces have to be bigger than the other?
For there to be acceleration, if not, F net would equal 0. Right?
What?
I don't know.
Okay, hold on though. Oh, I just ruined his brain for a second. That makes me happy. Say again what you just said. That means there's thinking happening. I'm not trying to ruin your life.
One of the forces, for this to have actual acceleration, like one of the forces like has to be greater, like FA on B has to be greater than FB on A.
Why?
Or else there'd be no acceleration.
No acceleration on what? Of what?
Of net force? Or no acceleration of A.
Okay, hold on. Okay, so here's the issue. This force here, force of B on A is acting on what?
B?
Force of B on A is acting on what?
A.
A, right? Force of B on A is acting on what? A, right? Okay, so this one's acting on A. Force of A on B, that's acting on
B.
B. So are either of these, or are both of these included on either box's net force?
No.
Say that again?
Yes.
Yes, say it again?
Yes.
Are both of these forces included on either one's net force?
F of B on A is included in A's and F of A on B is included in B?
Wait, they're not both included. No.
F net for the B is going to have this one, this one, right?
Yeah.
Not that guy.
Yeah.
Alright.
F net on A is going to have this one, this one.
Yeah.
Yeah.
Not this one.
Yes.
Does this make sense?
Yeah.
So these two forces really have nothing to do with each other in terms of an F net equation. A tension force will be the same on both sides. Because, let me show you why. Let's instead of having this stick that we can't really tell how much we're pulling, let's take a spring scale. Spring scale is used to measure force, right? Okay. So the lovely thing about it is it's going to measure it for us. So now I want you to hold this side. So if it's not really calibrated, but let's pretend that it's at 0. That's going to be our 0 point. Okay. If nobody pulls on it, then it's at 0. But if I start pulling on it, you have to pull on it too, right? Who's pulling harder?
Neither of us.
It's the what?
Same.
It's the same. It's the same. What is this measuring? It's measuring both forces. It's not measuring the force that you're pulling and not me, and not vice versa. Does that make sense? Okay? It's the same force. I have to pull with the same force that he has to pull with. Otherwise, one of us is going to give up. Are you with me there? Yeah, so get up. Oh man, hold on to this.
Hold on.
Okay, let's go. We gotta walk this way though.
Which way?
This way. Okay, so we're moving now. True? Yes, we're moving. Yay, we're moving little bits. And we're still pulling. Okay? So the fact that I'm moving or not doesn't really matter. Okay? We're gonna come back to this next time, but I don't want this to be a wasted conversation. So what I want you to do right now is to write that down on this piece of paper, like write on that problem. Write down so that we know that we decided just earlier today that F of A on B and F of B on A have the same magnitude. That is part of how tension works. Okay? We okay? Okay. Have a wonderful weekend, my friends.